So let me move on. Well, maybe the confusing thing about this problem is that we have this pulley rotation, pulley rotation, while M1 is moving toward left, M2 is going down, and the pulley will rotate in this direction, okay, with some omega. And the pulley, of course, as M2 goes down with some acceleration, okay, let's say call this A2, M1 will go again with some other acceleration, A1, and at this point, well, if this pulley would have only one radius, okay, and you would easily, in that case, say that A2 is going to be equal to A1. The acceleration of first block is going to be equal to the acceleration of the second block if we had this inner and outer radius of the pulley is the same. I mean, only single radius. The both strings are winded around the same radius. But it's not this. It's not true that they have different radii. So these A2 and A1, in that case, will have different magnitudes. Okay. Anyway, we will find some relation again, somewhat. We will find a relation between A1 and A2. Okay. Because whatever these accelerations, this pulley, both the inner radius and the outer radius, will rotate with the same angular acceleration. And this angular acceleration is related to A2. Okay. A2 is going to be alpha times R2, right? Because R2 is the larger radius. R2 is the larger radius. A2 is going to be alpha times R2. And A1 is going to be alpha times R1. Do you follow this? These are the two key equations. Okay, these are the important equations. Okay.
Yes.
And the other thing is that while T2 is pulling M2 up, and the same T2 is pulling the outer pulley down. Okay. And if we call this T1 that pulls M1 to the right, the same T1 will try to rotate pulley in this direction. And let's make also these, labels. T2 is acting on M2 in a different direction than it acts on pulley. It's action and reaction. Okay. So, well, this is a dynamical problem. Dynamics involves a rotation. So that means there is going to be two kinds of force equation. One kind is going to be linear force equation, and the other kind is going to be rotational force, which is torque. And there is going to be a torque, obviously, on the wheel. Okay. And the linear accelerations for M2 and the linear acceleration for M1, because they are not rotating, they will only have, linear motion. And solving this problem is attack every piece in this system. Your system consists of three different masses. One is two blocks, this one, this block, and this block, and the pulley. There are three pieces. So you have to write down three sets of equations. One equation, force equation for M1, one force equation for M2, and one torque equation for the pulley. So let's start with M1. So what kind of M1 motion, what kind of force is acting on M1? Well, first it is its weight downward and the normal force by the surface in the upward direction. And T1 is pulling it toward right. And next is frictional force is pulling it in the reverse direction to its motion. And m1 is going to be accelerated toward right. So with this, I can write down the force equation for m1, relating its acceleration to the forces. So obviously, in the horizontal direction, if you write down all forces in the horizontal direction, it's going to be mass times its acceleration, right? And what about the forces in the horizontal direction? It is T1 minus F m1 times a1. But what is F? Frictional force. It is mu times n, normal force, and normal force is just equal to m1g. So you know what the frictional force and how these forces are related to acceleration and the mass. This is the first set of equation. Let me write down this more explicit. T1 is going to be equal to T1 minus mu times m1g is going to be m1 times a1. So this is the first equation coming from first mass. What about the second mass? The second mass is pulled down by its gravity, and it is pulled up by the tension in the spring, the string. So it has simple equation. T2, sorry, since it is supposedly go down with the linear acceleration a2, m2g minus t2 is going to be equal to what? m2 times a2. And this is the second equation we get from the second block. And our third equation is going to be torque equation for the pulley. So I'm going to take this rotation toward right in the clockwise direction to be positive, okay? So in that case, T2 is going to be providing a positive torque, while T1 is going to be providing a negative torque for the pulley. But since supposedly it's rotating in the clockwise direction, the torque by T2 is going to be larger than T1, so it rotates, okay? Well, let's write down the torque equation. The total torque is going to be equal to moment of inertia of the pulley system multiplied by its angular acceleration. So as I said, the torque is T2 multiplied by R2, because T2 is wind around R2 and T1 is wind around the inner radius, minus T1 R1 is equal to I times alpha. Okay. So what do we have now here? We all know what the radii are. We all know what the moment of inertia and the masses are. And the only thing that we don't know is the accelerations and the tensions. So how many tensions do we have over here? T1 and T2. We have two tensions, two unknowns, together with the accelerations. But this A1, A2, and alpha seems that they are different things, but it's in fact they are not, right? They are all related to each other by these uh, auxiliary equations. We have two auxiliary equations relating all these A1, A2, and alpha together. So I will just leave alpha the only unknown among these three. And instead of A2, I can put alpha times R2, alpha times R2. And over here, A1, I will put alpha times R1. So you see, in that case, we have only three unknowns in these three equations. The first equation, the second equation, and the third equation. And three equations with three unknowns can be completely solved. No problem. You can solve for T1, T2, and alpha, because the other parameters are known. Buraya kadar okey mi? Her şey.
Buraya kadar okey hocam, sıkıntı yok.
O zaman yani so how can we solve this? Okay, let me try to do this. The play with first and second equation. I will let me erase this part since I know now the only important thing about me about the problem is just these three equations. Okay. So what I will do now is I will make some tricks. I will multiply the first equation by R1 every term. Okay. R1. Well, this is going to be R1 squared and this is R1 T1. And I will multiply every term, the second equation, by R2. Okay. R2 minus R2 times T2 and R2 squared. And I will add this first equation and the second equation side by side. Okay. So if I add, uh, let me rewrite this second equation over here. Minus T2 times R2 is equal to M2 alpha R2 squared, right? Minus M2G times R2. So erase this and come over here. Let me write down this first equation. T1 times R1 is equal to M1 alpha R1 squared plus, I'm just shifting this to other side, mu times M1G R1. Okay, so this is also gone. And the first and second equation, add them side by side. Okay, I get T1 R1 minus T2 R2 on the left hand side. On the right hand side, I get these. Can we make some simplifications or maybe parentheses? Well, no. M1G and 2G. Just right away. Everything. M1 alpha R1 squared plus M2 alpha R2 squared plus mu M1G R1 minus M2G R2. But the left hand side is just minus I times alpha, right? So this one is minus I times alpha. All right. And if I rearrange again everything so that I collect all alpha terms on the right hand side, that means this is minus I alpha. I collect all alpha terms on the right hand side, alpha, make a parenthesis m1 r1 squared plus m2 r2 squared plus, I can erase this now, right? Plus I, and yeah, I got this to the other side, m2g r2 minus mu times m1g r1 is equal. So alpha is going to be m2 g r2 minus mu m1 g r1 divided by m1 r1 squared plus m2 r2 squared plus I. So this is the solution for alpha. Okay, so I can erase this whole thing. Once I know alpha, I can calculate all the rest. But before that, let's first try to calculate the numerator, because I expect that this numerator should be positive. If it's not positive, the system will not move, because the friction will overcome. The friction between the M1 and the surface will overcome, and the system will not move. If this numerator is negative, if it is positive, then the system will move. M2 is going to go down, and M1 will go toward right, and this will rotate toward the clockwise direction. Let's do this. M2G R2. So M2 is 2, G is 10, R2 is 20. 2, 10, 20, 20, 400. Minus, this is 0.4, M1 is 1, G is 10, and this is 10. 10, 10, 100, multiplied by 0.4, it's 40, right? 100, 0.4, it's 40. So that's positive. So the system will move. Okay, this is positive. Denominator, this is positive. So this system will move, and the rest is just find alpha numerically, and we can put all quantities over here. M2 is 2. This is 10. 20 multiplied by 0.2. 20 multiplied by 0.2 is 4. 4, right? Yeah. Minus, M1 is 1, 10, this is 0.1, 1, 0.4, divided by M1 is 1, R1 is 0.1, 0.1 square is 0.01, plus M2 is 2, R2 is 0.2, right? 0.2 square is 0.04, multiplied by 2 is 0.08. And the moment of inertia given in the problem, it is 0.41 plus 0.41. And this will give you alpha, the value of alpha. Once you know alpha, you can calculate A1 and A2. But the problem over here is T2, right? And how is T2? How can I calculate T2? If you remember the equation for T2, the equation for T2 was M2G minus T2 is equal to M2 times A2. So T2 is going to be M2G minus M2A2. And M2 is 2, it is 10, 20, minus M2 is 2 multiplied by A2. But A2 is alpha times R2. So 2 multiplied by alpha times 0.2. Well, whatever this alpha value that you calculate from here, put over here, you calculate T2. Okay?
Tamamdır hocam. Teşekkür ederim.
Okay. So, how many questions I have? Let me check. How many questions unsolved? This one, and this one. 3 questions. Okay. Let me go quick. All right. So this is one question. Force is given 2 newtons in the x direction, 3 newtons in the y direction, acts on a 5-kilogram object, and as it moves in a straight line from the position 1 meters in x, 1 meters in y, to a different position 4 meters in x and minus 1 meters in y, determine the work done by this force. Well, we know the work done by the force is the force vector dot product with the displacement vector. Well, displacement vector, you can easily calculate with the given values. This last position minus the initial position. Last position is R2. The x component is 4. Subtract this 4 from by 1, it is going to be 3i. And minus R1. Sorry, pardon. Yeah. The y component of R2 is minus 1 minus the y component of R1, 1, so minus 2j. Okay? If you subtract R2, R1 from R2, you get this. So in this equation, just write down the force 2i plus 3j, dot product with 3i minus 2j. So you have to know the multiplication between the unit vectors. I dot I is 1, I dot j is 0, j dot I is 0, j dot j is 1. So with this, multiply the first components, 2 times 3 is 6. Multiply the second components, 3 times 2 minus 2 is minus 6, it is 0. This work done by this force is 0. Okay.
Hocam ben tamam anladım da ben bu soruda şey yapmıştım. İşte ok çizerek bir şeyler göstermişim.
Evet.
Etki eden kuvvet onun hareket yönüne tersti. O kısmı anlamamıştım.
Hareket yönünün ne olduğunu nereden biliyorsun?
Ya vektörü çizmiştim işte. X'ten 2, Y'den 3 birim kuvvet için.
Evet. Şimdi bak, mesela diyor ki tamam, birinci pozisyon R1 işte burada olsun. İkinci pozisyon R2 burası olsun. Dolayısıyla R2 minus R1 ne olacak? Buradan buraya olacak değil mi? Şu vektör. Bu delta R.
Evet.
Delta R'la şu F'yi çarptığında 0 veriyorsa F kuvvetinin delta R'a dik olması lazım.
Anladım. Yani iş yapmıyor. Tamamdır hocam.
Dik bu 0. Evet. Çünkü ikisi de sıfırdan farklı. İkisi de sıfırdan farklı iki vektörü çarparsan 0 veriyorsa mutlaka bu iki vektör birbirine dik demektir. Okay. The next question. All right. The next question is again a rolling motion. A 4 kilogram in a radius of 10 centimeters, a solid sphere is moving down, I think, from a inclined table, and the angle of the inclination is 45 degrees, and it is released from rest from the top of the inclined angle, and it is rolling down to the bottom, and it gives. So the problem is asking about what is the frictional coefficient, okay, between this solid sphere and the inclined table. That's an interesting question. So let's draw the picture. Well, this looks like one of the problems that we have solved today. And it is rolling, and the center of mass is going with the linear acceleration, of course. It's a sphere. It is rolling with some angular acceleration, alpha. Okay. It's a solid sphere. It has a moment of inertia, I. It has also mass, m. So all you have to do is, okay, you just write down the dynamical equations for this rolling sphere. It is 45 degrees. Well, what are the dynamical equations? What kind of motion does this sphere do while it's rolling down? Its center of mass is just doing a linear accelerated motion, right? So I can write down a force equation for the center of mass. The force equation for the center of mass means that if you take this axis x to be a parallel to the inclination angle, in the x direction, all forces, linear forces acting on the rolling sphere is going to be just equal to its mass times linear acceleration. But what is this? Well, since it has this mg in the horizontal direction, in the x direction, mg has the component mg sine 45 degrees. And obviously we have a frictional force which is in upward direction, minus F is going to be m times E. This is the force equation for the center of mass of this rolling ball. But of course, we have a second degree of freedom for the motion. It is rolling, it's rotation. And the rotation takes place because there is some torque. And I have to write down the torque equation. The total torque is going to be just equal to moment of inertia of the solid sphere multiplied by alpha. It's angular acceleration. But the thing is, the linear acceleration and the angular acceleration, again, is always related to each other. They are not independent from each other because this is a rolling. It is going to be alpha times r. R is the radius of this sphere. So instead of alpha over here, I can just put A divided by R. And what about the torque? Since the sphere is rotating around this axis, and I have to find out which forces are applying a non-zero torque around this point. Well, obviously, mg sine theta is not going to give a torque for the rotation of this because the force is applied just to the center of rotation. You know, the torque is just force multiplied by the vertical distance to the center of rotation. But since the center of rotation is just zero for mg sine theta, which is acting on the center of mass, this mg sine theta cannot produce a torque for this rotation. Only torque which is produced by is going to be the torque produced by the frictional force between the sphere and this frictional force. And so this torque is going to be just F times R. The frictional force is just A divided by R. And we can just solve this equation for F. It is going to be a moment of inertia multiplied by linear acceleration divided by R squared. But I is given 2 divided by 5 mr squared. So this is going to be, F is going to be just 2 divided by 5 m times A. So for this rolling motion, I just got the frictional force in terms of its acceleration and the mass of the sphere. But the problem is asking me about the coefficient of friction. So let's first find out what A is, because without finding A, I cannot find the coefficient of friction, because frictional force and the normal force that the surface is applying on the solid sphere is just mg cosine 45. This is something you know from chapter 5, okay? So the frictional force is just the coefficient of friction multiplied by n. So on the other hand, the frictional force, apart from this equality, it is equal to this one, mu times mg cosine 45. Okay, but we don't know what A is. So first, let's try to find what A is once I replace this in this equation, mg sine 45 minus 2 divided by 5 ma is equal to ma. I can pass minus 2 divided by 5 ma into the other side, making this 7 divided by 5 ma on the right hand side. So A is going to be just cancel m's, 5 divided by 7 g times sine 45. Okay, so I got this A. and F in terms of A, and F in terms of coefficient of friction. I will just bring all these together. This mu times mg cosine 45 is equal to 2.5 m times A, and A is 5 divided by 7 g times sine 45. So I'm just put, instead of A over here, 5 divided by 7 g sine 45, making this frictional force equal to 2 divided by 7, all right? 2 divided by 7 mg sine 45. So what do we get over here in the last equation? Both these mg's may cancel out, and I can cross cosine 45 to the other side as division. So I'm just having mu on the left-hand side, the coefficient of friction. The coefficient of friction is just equal to 2 divided by 7 multiplied by tangent 45. That's it. This is the solution of the problem. Okay? Because the problem is
Teşekkürler hocam.
asking a coefficient of friction. Okay. All right, so let me quickly erase this and move on. I think this is going to be the last problem for today. Next problem is this one. So, I think it's yeah, it's about power. 60 kilogram, so sorry, 600 kilogram block is moving on this inclined surface. The inclination angle is just 30 degrees, and there is this external force P, which is 4,000, which is given as 4,800 newtons applied, and it's applied in the horizontal direction. Okay, and it is moving this block from this initial velocity of 1.3 meter per second to the final velocity of 2.9 meter per second. And the question is, what is the power delivered by the external force P during a time interval of 5.4 seconds, when the time it takes from velocity v1, going from velocity v1 to v2 is 5.4 seconds. Okay. So, solving this problem requires finding the work provided by this force P to this system of block that goes upwards in this incline. Okay. You will have only have to find the power, the work done by P. Okay. Work done by P is the application of this P force in the direction of motion, the component of the P force, sorry, in the direction of motion. Let me draw this. Why I'm drawing this? Okay. I have to draw this parallel. I have to draw this parallel to the inclination angle. So this P cosine 30 degrees, right? This is the component of the P force in the direction of motion. Component of the P force in the direction of motion will make some more, will do some work, right? And this work done by P force is P times cosine 30, okay, And that force is applied only a distance of 3 meters, because finding the work, we just what we do is we just multiply the component of the force which is in the direction of motion by the distance that the object goes. So I multiply this by 3. We know everything over here. The work done by P force is just P, which is given 4,800 newtons. Multiply this by cosine 40 degrees, cosine 40, and multiply by this 3. This is the work done by P force. But the question is asking the power by this P force, okay? The power by the P force, the power, by the definition, we know that the power is just work done by that specific force divided by duration. And duration is given. And the work is just can be calculated from this expression, and divide this expression by just 5.4 seconds. That's it. It is going to be power, and the unit for power is just watts. And I'm just leaving to calculate, the result to you. It's just you plug and check these numbers in your calculator. And this was the last question, okay?
Hocam
Yes.
şimdi bu soruda da V1, V2 vermiş ya. Onları kullanarak çözmeye çalıştım. Çözemeyince inat ettim.
Evet.
Sonra öyle kaldı.
Şimdi güzel. Bu sorun iyi oldu. Çünkü niye? V1 ile V2 kullandığın zaman ne olacak? Şimdi V1 ile V2 arasında, yani diyelim ki buradaki kinetik enerjiye K2, buradaki kinetik enerjiye K1. Şimdi iş enerji teoremi diye bir şey var. Work enerji teorem diye bir şey var. Work enerji teorem diyor ki bir cisim üzerindeki yapılan tüm kuvvetlerin işi var. Dikkat et. O cismin kinetik enerji değişimine eşittir. Yani işte K2 eksi K1. Şimdi sen K2 eksi K1 hesaplayabilirsin. V1, V2 vermiş. Sonra dersin ki ya ben bu ikisinin farkını alırsam yapılan toplam işi bulabilirim. Yapılan toplam işi de delta T'ye bölersem power'ı bulabilirim. Burada çakarsın. Niye? Çünkü
Potansiyel de var değil mi hocam burada?
bu work'un içerisinde yer çekiminin yaptığı iş de var. Yer çekimi burada negatif iş yapıyor. Sadece P kuvvetinin yaptığı iş yok. Eğer buradan yola çıkarsan, hesaplarsan W bölü T'yi, burada çakarsın. Yanlış bulursun. K2 eksi K1'den. Çünkü burada yer çekimi artı P kuvvetinin yaptığı işi hesaplıyorsun. Onu zamana bölüyorsun. Power hesaplıyorsun. Yanlış. Burada problem de sadece P kuvvetinin yaptığı power'ı, P kuvvetinin gücünü soruyor. O yüzden sadece P kuvvetinin yaptığı işi hesaplayacaksın. Burada da yol var. P kuvvetinin bileşeni var. Bunu şeyleri kullanmadan yapabilirsin. Buradaki hızları. Gerek yok zaten. Onları vermesine gerek yok. Sizi şaşırtmak için vermiş o hızları. Anlaşıldı mı? Burada dikkatli olmak lazım.
Tamamdır hocam. Peki hocam o kütlenin aşağı doğru yaptığı bir kuvvet var ya eğimden dolayı. Hani mg çarpı sin 30 olacak. Aşağı doğru bir kuvvet var yine.
Tabii aşağı doğru yer çekiminin yaptığı kuvvet var. Evet.
Onu çıkartmayacak mıyız P'nin yaptığı kuvvetten?
Hayır.
Hani F netle çarpmıyor muyuz?
P'nin gücünü soruyor ama. Hani
Anladım.
hangi kuvvetin gücünü soruyorsa sadece o kuvvetin yaptığı işi hesaplayacaksın. Ondan sonra zamana böleceksin o kuvvetin power'ını bulmak için. Sen
Tamamdır.
yine mg sinüs θ ile yine yer çekimini işin içine katmaya çalışıyoruz. Onu katmıyoruz.
Tamamdır hocam.
Yani check etmek için tabii şunu yapabilirsiniz. Şimdi P kuvvetinin yaptığı işi hesapladım. Bize buna yer çekiminin yaptığı işi hesaplayacaksın. Sonra bu işleri toplayacaksın. Sonra da kinetik enerjinin değişimine bakacaksın. Sağlıyor mu bunu? İstersen yani sadece sağlama yapmak için bunları yap. Yani sağlayıcı
Tamamdır hocam.
zaten göreceksin. Okay. So guys, that's it. I mean, this is the end for today.